Okay, today we start a new week, Dice Playing God. It's a wordplay for the famous quote by Einstein, God does not play dice, meaning that he thought that there cannot be an intrinsic stochasticity in nature and its laws, right? So basically, he proclaimed his disbelief in quantum mechanics, right? Although he used it very well to solve some problems. And I actually yesterday added, or the unexpected virtue of ignorance. Have you watched Birdman? Yes. It's the subtitle. Yeah. Yes. So this is it. This is the slide for this week. And the rest I will just simply write down, okay? So maybe I should make it bigger. So let me first start asking you whether you have heard of Lagrange, I hope I'm writing it correctly, multipliers. Have you heard of this? Anyone? Some of you? Yes. What is it used for? Optimization. Constraint optimization, right? We will use it in a moment, so I want to basically describe it with a simple example, okay? Let's say you have a rectangle that has a side x and y. Basically, let's say you have a wire that has a length x plus y equals 1 over 2. Or let's say you have a wire that is 2 meters long, so x plus y is 1, okay? Are you with me? What is the biggest area that you can make from this wire? That's the question. You understand the question? Yes? So what is area? Area is x times y, right? So Lagrange multipliers use, so in the case of Lagrange multipliers, you define something called L, let's say, which has the thing that you are looking for, x times y, minus lambda times this equation, expressed in the following form, x plus y minus 1 equals 0. So whatever you have here, you plug in here, x plus y minus 1. Okay? Then you do the optimization. Do you know this? So how do you do normally optimization? You take the derivative and set it to 0, right? So what do you get? If del over del x is 0, you have y minus lambda equals 0, which means y have to be lambda, right? You can also use del L over del y equals 0. What do you get from here? X minus lambda equals 0, which gives you x equals lambda, right? So remember, x plus y is 0. X plus y is 1. So lambda plus lambda is 1. Lambda equals 1 over 2. So the best area that you can get, you reach it when they are all equal to lambda and it equals to 1 over 2. Okay? So now we will use it in something totally different. So this was an introduction to Lagrange multipliers, okay? Now let's talk about the following. Let's talk about coin flip. Okay. Let's say you flip a coin 10 times. Okay. And there are two observers. One of them is a microscopic observer. Okay. Which that observer knows each flip 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will make sure what I mean by each flip. So one observer knows that it's heads, 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 heads. This is the first observer. This is the knowledge of the first observer. Let me remind you, we are going towards the unexpected virtue of ignorance, okay? The other observer is ignorant. He only knows how many heads there are, okay? So how many heads do we have? 10 heads, 0 tails, right? So if we compare the knowledge of two observers, they know the same amount. They have the same amount of knowledge. Why? Because the observer, the macroscopic observer, knows that there has been 10 flips, right? And if you have 10 heads, then each flip is head, right? Now let's do the same experiment, but this time one of them, let's make one of them tails. So the microscopic observer knows exactly which one is tails, right? The macroscopic one now has the knowledge of 9 heads and 1 tails, but she doesn't know which one is tails. So what was our ignorance before? It was 0, right? Now, how much ignorance do we have? Let's call it 10, because there are 10 different possibilities, okay? Now, if you have 2 tails, right? 8 heads, 2 tails. How many different ways can you rearrange these tails? 90? Yeah. 45, 90. Okay. I trust all of you, but the point is that it's bigger, right?
Yeah, it's more.
Right? So where I'm going with this, I'm going with this towards thermodynamics, believe me or not. Okay. So as the number of when is the maximum ignorance occur? When do you have maximum ignorance?
5 heads, 5 tails.
Yes, 5 heads, 5 tails. Okay, are you with me, everyone? Yes. This is not new to you, right? So let's now think about thermodynamics. Let's say you have an ideal gas. Okay. And before even we go there, let me just, before we go to ideal gas, let's have, let me think. Let's have rooms, okay? Again, the same problem. Let's have rooms. And I have n particles. And I want to put them in these rooms, okay? How many different configurations do I have? n factorial, very well, n factorial. Now, if I ignore, if I can put some particles in the same room, okay? And this time my ignorance is that I can only count how many particles there are in one room. That's the macroscopic observation. The microscopic one knows where exactly each particle is, but the macroscopic one knows which room has how many particles. Do you understand my point? Yes?
Yes.
Yes, you can ask
Is
some.
n factorial when there's n rooms or that's what I was wondering.
I also wanted to skip that, but okay, n particles, n rooms. Okay, so if this one has, for example, n1 particles, okay, then the bigger one, the macroscopic one, loses some information because they can be rearranged in different ways, right? Then you can continue this like that. Okay, this is the number of different configurations. What happened? Nothing happened. Number of different configurations, and this goes until the end. Okay. By the way, let me clarify that this subject is right at the edge of my knowledge. Okay. So any help is appreciated whenever I fail to understand something. Okay, so basically this is the number of different configurations, and I want to actually know the probability. Well, I want to go to this, I will skip a lot of things. I want to go towards here. Have you seen this before? It's entropy, defined as probability of each state times ln of the probability of each state. So let's briefly try to understand where it comes from. Okay? So if I take ln w, what do I get? Ln n factorial and 1 factorial minus ln n2 factorial, etc. Right? But n factorial has a nice expression. Like, for example, ln n factorial corresponds to, you can write it as ln 1 plus ln 2 plus ln 3 until ln n. Do you agree? Yes? So it's actually the integral of ln x dx. Right? What is the integral of ln x? No, 1 over x integral is ln x. What's the integral of ln x? X ln x. For some reason you know this. That's good. Yes, that's correct. X ln x minus x. You have this 1 and n, so you will have, okay, I go from 1 to n, right? So I will have an expression for something like n, then ln n, minus n, minus what is, if I put 1, then I will get 0. And I have plus 1, but I will ignore it. Okay?
The numbers that we deal with are only integers.
Yes.
Integral.
Yes. So today we will do it that way, like You will just trust me with everything. Okay, let me really answer your question. It works if n is very large. Then you can think of each one integer as infinitesimal. So it corresponds to integration. Okay, so you have n ln minus n. Do you see it, everybody? Good. Then what is ln w? Do you see that it has to do with n ln n minus n1 ln n1, like there is a sum over I minus ni goes to some n. Do you understand my point? Yes? So I want to do something with this. So I had different configurations and I took ln of it. Why I took ln? Because I want to be able to sum up probabilities while multiplying them. So, for example, in the future, I will look for what is the possibility of getting A given that I had B. They are independent. Okay. Then probability of, do you write it this way? Yes? Is this correct? Then what is the correct one? Okay, can I say that probability of A plus B happening, like A and B happening, can I say that it's probability of happening, probability of A and times probability of B? Yes, I can do that? Yes. See, I don't know many things too. So that's why we are taking ln, because if it is related to ln, then ln A times B corresponds to ln A plus ln B. So whatever I will get, I want to be able to sum them up. Okay. Now, do you remember our first problem? Yes.
Is the above notation correction would be like PA plus PB equals PA times B? Or am I making up?
No, it's like probability notation is not correct. Okay, but what I mean is probability of both A and B happening is probability of A times probability of B. Okay, this is going exactly as I expected it will go, but never mind. I don't mind showing my ignorance. Okay, so if you don't understand it, it's perfectly possible. Never mind, but I want to show you some stuff. For example, this heads and tails. Can we show that when they are equal, that's the maximum probability? Can we prove it? Yes, we can. So let's say this time you have n different rooms. This time for sure I know that I'm talking about the rooms. Okay. Room 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's say that I know that the probability of being here is P1, probability of being here is P2, etc. So what is my total information? So I will ignore this term because it's a constant related to the total number of particles. I will use this one. Okay. what is S? It is defined as, sorry, okay. Are you with me? Yes? So I want to find the maximum of S, the maximum of ignorance, okay? But there is a constraint, right? What is that constraint?
So what do you mean by constraint?
Do you remember this x plus y has to be equal to 1 in the beginning, Lagrange multipliers? What is the constraint for probabilities? It has, the sum has to be 1, right? So I have this formula. Yes? Now, what is my Lagrangian? It's minus I1 to n pi ln pi minus pi plus, no, minus lambda times nothing else. Do you agree? Yes? So if I take, sorry, if I take del L over del pi for and derivative with respect to any pi, what do I get? Any ideas?
First one is just ln pi, right?
Ln pi. Do you agree? The first one, because you just said that the integral was this one. So the derivative is ln pi, right?
Minus.
Minus. What is the other one? Minus lambda, right? Equals 0. Do you agree? So what do I get from here? Ln pi is equal to minus lambda. Is that correct? So pi is equal to e to the minus lambda. What does it mean? Anyone?
Probability decays as lambda increases, right?
Lambda is just a quotient, right?
So it's equal for all of them.
Yes, that's what it means, right? So you get the maximum ignorance when you have P1, probability of being in the first room equals probability of being in the second room, etc., equals some constant. And that constant has to be 1 over n, because they have to sum up to n. Do you see we started badly, but we have reached to some good points, right? Do you agree? I hope you do. So let's continue. And this time, let's look at an ideal gas this time. Okay. So ideal gas, and it has particles in it moving in all these directions, right? Let's say the ignorant observer only cares about how many are there particles at each energy range. For example, there are some rooms for the energy, okay, and over here, let's call it room number 1, which is between 0 and some dE. There are n particles, okay? there is a probability of having being there is PE. Like, for example, if you are between E and E plus DE, that's better, that's more physical explanation. Then probability of being there, a particle being there, is PE. Are you following? Everyone is following? Yes? So now again, I will write S as minus sum of P EI ln P EI minus P EI. Okay? So what are the constraints? First one is the obvious one. Can you tell me?
So the probability at zero energy is zero, right?
No, what is the first constraint when you talk about probability? Yes, the sum of PEI has to be 1. Okay? Now, what else is conserved in here? Total energy, right? So how can you find total energy?
Sum the energy of the particles.
Exactly. So this probability of being at energy EI times the energy EI will give you the average energy, and it has to stay the same because you are not losing any energy to nowhere. Are you following, everyone? Yes? So how can you find the maximum of S? We are doing a very serious business. The man had to kill himself, right? Boltzmann, to convince people of this. So I'm sorry that I'm not doing it very well, but you are getting the idea, I hope, right? Okay, let's write down the Lagrangian. Now we have two constraints, so we need two coefficients, right? So I have minus lambda times this. Do you agree? And I also have minus beta times do you agree? Everyone? Yes? So now let's take the derivative with respect to what? Energy. Okay, sorry. Oh, what happened? So can you help me out with this derivative? Please. We don't know. It's a coefficient. It's a Lagrange multiplier, right? It's a mathematical construct for now. But it will turn out to be something really interesting. Okay? I promise. So what is the derivative of the first term? ln PEI. Everyone agrees with this?
But we don't know how P is a function of EI. It could be EI squared or something, right?
So you need also this.
Yes.
Yes?
Yeah.
Mm.
Or we are taking derivative according to TE,
Let me think. Maybe let's take the derivative with respect to PEI and see if it doesn't go where I want it to go. So I will take the derivative with respect to this. Then everyone is happy with this? Yes. So then I have minus what? Lambda? Lambda. What else do I have?
minus beta E of I.
Yay. Yay. Okay? So this has to be 0. So ln PEI is something like minus lambda minus beta EI. Right? So what is PEI? It's something like e to the minus lambda times e to the minus beta EI. Do you see it? Yes? So I can basically say that PEI is some constant times e to the minus beta EI. Do you see it? So this was first realized by Boltzmann. So you can see that the probability of being at any energy is related to exponential minus some constant times EI, right? Later on we will not discover, but I will tell you that beta is equal to 1 over kBT, the temperature, right? So basically you get the Boltzmann distribution. So then let's go back to ideal gas. When you reach maximum ignorance, right? That's how we got this. Then you have probability of being at any energy is related to e to the minus that energy divided by kBT. You have seen this in many physics applications, right? Like finding the number of voids, what they were called? Impurities, etc. But let's keep our view on the ideal gas. Do you have any questions so far? Anyone? No? Now let's find the distribution of velocities. Okay? Can we do that? So what I will do is I can have some Vx, Vy, or Vz, right? And if I'm at a certain speed, the radius of this one is the speed. Do you have any questions so far? If I'm at a certain speed, then my energy is mv squared over 2, right? Kinetic energy. So this means that a certain speed corresponds to a certain energy, right? So what is the probability of me being at this speed? How can I find it? What I can do is, if I integrate, so I'm looking for something like probability of being at certain speed, dv, and if I integrate it, I should get 1, right? Something like this. So how would you integrate this probability? you could integrate it, probability of being here times the volume of that one, right? So basically you can do 4 pi v squared dv times e to the minus mv squared over, okay, 2 kBt. Do you understand what I just did? I plugged in this energy over here. Everybody follows? No? So if I'm inside this spherical shell, then I have energy E, right? What is the probability of having energy E? It's e to the minus e over kBt. If I'm at that velocity, what is the energy? mv squared over 2. Then I just plug it in here. Like volume of this shell times the probability of being at that shell. If it's not, yes. Hmm?
Is it volume or area?
It's volume because it's area times the thickness, right? So I'm unrigorously going towards saying that PV, probability of being at any velocity v, is related to v squared times e to the minus mv squared over 2 kBt. Okay, this is what I'm trying to do. Do you have any questions so far?
So what are
Yes.
the limits on the velocity?
0 to infinity.
And
Okay.
negative.
This is speed, so it is not negative. Thank you for that question. Do you understand my point? Of course, to have some real definition of probability, you have to have some coefficient derived in such a way that if you integrate it, it gives you 0. 1. 0 to infinity. Okay? You can find that coefficient in books, in Google, everywhere. Okay? But that's not the point. What if I have 2 dimensions? What if my gas is wandering around in just 2 dimensions? What do I have then? Yes, you have a circle and you have v dv over here. So your probability will be related to 2 pi v times e to the minus mv squared over 2 kBt. Do you agree? So the probability in 2 dimensions is related to v times e to the minus mv squared over 2 kBt. So today, what I wanted to show you by really putting an ideal gas inside a computer and see whether the entropy really increases and reaches maximum, and whenever it reaches, whether you have this distribution or not. Okay? And let me show you that I have a working code that produces this, but I just have 10 minutes, so I will not, instead of explaining it, I will start something totally new. I mean, I will start with boundaries, with the collisions and etc., and we can do the rest in the coming lectures. Did I absolutely confuse you today? Yes? I hope not. So let me just show you the working code. So you can see that no matter what the velocity distribution was at the beginning, it quickly approaches to this Maxwell-Boltzmann distribution. Okay? And I didn't cheat. I really put particles inside the box and they are really colliding. Let me show you that they are. So I will show you the collisions. No. Let me show you with a few particles. There are 1,000, so plotting is an issue. Yes. Do you see them colliding with each other? Yes? And what we are going to do is we are going to actually code this, okay, properly, and the collisions with the wall, and we will not do anything else, and the system itself will move towards the maximum entropy and will settle on this nice curve, and it will be there forever.